How's it going, Professor Lamond? I'm Shane Cooke, and here's my signature. So our problem statement is, water is pumped from the large tank shown in diagram A. The entrance to the pipe section is sharp-edged, and the pipe is cast iron with a total length of 2 meters. Flow within the pipe is observed to be fully turbulent. The relationship between volumetric flow rate and actual head rise is provided in the pump specifications and is shown in diagram B. A, determine the volumetric flow rate for the system. B, show that the observation of fully turbulent flow was correct. And C, if the pump is 70% efficient, determine how much power must be supplied to the pump. So I'll start by quickly drawing a picture of what our pump and pipe looks like. So here's our pipe, this is our reservoir, that's our little pump, and this has open flow. There's our pump. The diameter of our pipe is equal to 0.07 meters. And this is our tank, which is open to the atmosphere, and the height from the top of the water to the center of the pipe is 6 meters. So what we're given is that the length of the pipe is equal to 2 meters. And when we look up cast iron in our textbook, the friction factor, sigma, is equal to 0.26 millimeters. And we are also given that the relationship of head gain to the volumetric flow rate is, head gain is equal to 20 minus 2,000 Q squared. Okay, so if we start with Bernoulli's equation, we have that the pressure at 1, well, first we'll specify which is 0.1 and 0.2. So 0.1 is going to be up here at the top, and 0.2 is going to be right there at the exit. So pressure at 1 over gamma plus volume 1 squared over 2g plus z1 plus the head gain of the pump is equal to pressure at 2 over gamma plus v2 squared over 2g plus the height of 0.2 plus the major head losses. So there's a couple things we can cancel out here. Since 0.1 is open to the atmosphere, this is going to be equal to 0, and since this is a large tank, the velocity at 1 is negligible, so we can say that that goes to 0 as well. Same thing for 0.2. This is a free flow pipe, so it is open to the atmosphere, and pressure at 2 will go down to 0, as well as the height of 2 is going to be our starting height, so we can assume that to be 0 as well. So we're left with the height of 1, which we know, the head gain, which we don't, the velocity 2, which we also do not know, and the head loss, which we can calculate. So we are trying to find, for part A, is the volumetric flow rate of the system, which is Q. So we can write all of these things in terms of Q so that we only have that as our unknown. So HP, we have 20 minus 2,000 Q. Velocity 2 is the same as Q over the area. And we also have the equation for head loss is the friction factor, the length over the diameter, times velocity squared, which is the same velocity over 2g. So both these velocities are going to be equal to Q over A, and A is easily calculated. So if we combine all these things and plug in what we do know, we have that 6 plus 20 minus 2,000 Q squared is going to be equal to V squared, which is Q over A, which is the same as Q squared over A squared 2G, plus head loss, which is the same as F L over D Q squared over A squared 2G. So we then can pull out the q squared over a squared 2g on this side to make things easier for our eyeballs. Add these, 26 minus 2,000 q squared is equal to q squared over a squared 2g. So clear. And then all that multiplied by 1 plus FL over D. Okay. So now the only thing we don't know is the friction factor F, but we can find that out from the Moody diagram in our textbook. So if we take sigma and divide it by D, that ratio is equal to 0.00026 over 0.07. And that's going to be equal to 0.0037. And since this was observed to be fully turbulent, when we go to the Moody diagram, we need the Reynolds number, but since it's fully turbulent, it's going to be at the point where it is fully horizontal and is all flattened out. So the Reynolds number is not needed for this step. So looking at the Moody diagram, we can find that the friction factor F is equal to 0.028. I'll make a note that that's from Moody. All right, now we can just plug in all the numbers and solve for Q. So we have 26 minus 2,000 Q squared is equal to Q squared over area of the pipe, which is pi over 4 times the diameter squared, all that squared, times 2 times gravity, which is 9.81 meters per second squared, and multiplied by 1 plus F, which is 0.028, times L, which is 2 over diameter, which is 0.07. So now this whole side will give us, right, this 26 minus 2,000 q squared is equal to 6,194.433 q squared. Quick algebra, add over the 2,000, 26, go to 8,194.433 q squared, divide the 8,000, and we have q squared is equal to 0.00317. And then square root both sides, and we have q is equal to 0.056 meters cubed per second. Now for part B, this is asking, show that the observation that it's fully turbulent flow is correct. And since it was fully turbulent, so I'll write just a little note here. Since the flow within the pipe is fully turbulent, the Reynolds number was not needed. And that way, because we weren't given the initial velocity or the velocity in the pipe, which we could have used to then find Reynolds number, but we did not need that. So since that was unneeded, we can prove that it was fully turbulent. All right, so now quickly do part C. And this is if the efficiency is equal to 70%. So the equation for efficiency is equal to rho times g times density times gravity times flow rate times the head gain over, this is the ideal work or power given, and this is W dot shaft. So this is This is ideal. And this is actual. So if it was 100% efficient, the ideal would be equal to the actual, and we would have a ratio of 1 here. But obviously it is 70%, so this is 0.7 is equal to 999, which is the density of water, times gravity, which is 9.81 meters per second squared, times Q, which we solved to be 0.056, and head gain, which we have in terms of Q, which is 20 minus 2,000, 0.056 squared. And all that over W dot shaft. So this whole big mess will give us that 0.7 is equal to 7,537.5 over the power output, and add this to this side, divide to the other side, divide by 0.7, and our actual power that is supplied to the pump has to be 10.77 kilowatts for a 70% efficient pump. Thank you very much, and I hope you enjoyed.